Hello, everybody. Welcome back. We're going to continue on with our last three presentations of the day. And so will everybody join me in welcoming up our next presenter, Dubem.
Okay. Thanks, Tyler. Everybody, welcome back from the break. Once again, my name is Dubem, and I'm going to be talking about optimizing lineups for daily fantasy football. Okay, so I will be talking about the 50-50 competition. In specific, I won't go over what daily fantasy football is or how it works. I'm going to assume most of you are familiar. But the 50-50 competition type is one where participants in the top 50th percentile of all performers all receive the same payout, and those in the bottom 50th percentile receive no payout. And so, given these rules and the context of optimizing lineups, it might feel like a pretty good strategy is to maximize the projected points of your lineup, given that you have projections for what each player is going to score. And that is a pretty good strategy, but there are some issues with the strategy. The first being that our projections are inaccurate. I know mine are. I didn't actually come up with my own. I asked a buddy, Caleb Nelson at dfsforecast.com, for his projections, and he's won the DraftKings Millie Maker competition several times. So his projections should be pretty good, but the R-squared on his projections are around 0.6, okay, which is, I believe, right in line with industry average, the ESPNs of the world. Okay, so none of us are all that good. And given that we're not very good at projecting points, we don't really get any reward for the risk of taking on those projection inaccuracies. And so to illustrate what I'm talking about, I have a toy scenario up there. Let's say we have two lineups. Lineup 1 is projected to score more points than lineup 2, but lineup 1 is also more variant than lineup 2. And so given where I've drawn the payout line there, you would go with lineup 2 over lineup 1. And you'd go with it because you get paid out more often. So really, the strategy is to maximize the expected payout and not the projected points, which is pretty clear. And people do that. But dealing with that expectation function in a rigorous way is pretty challenging and computationally expensive. On honestly pretty good hardware and pretty good, like a commercial solver, these things can take minutes to solve at a time. And for my buddy at dfsforecast.com, users aren't going to wait around minutes to optimize a lineup. They want it the second they hit the optimize lineup button. And so is there a way that we can speed this process up? And the answer is yes, or else I wouldn't be up here speaking. And what we can do is we can come up with a proxy goal. If you look at the toy scenario again, what we can do is we can just try and push as much of the probability distribution above the payout line as possible, or we can maximize the worst case scenario. And there is an optimization paradigm that does just that, called robust optimization. So I'll go through how it works, how to set the problem up. Okay, so first we're going to start with that basic strategy. That's what I've called mixed integer linear programming there, where you're trying to maximize the projected points, which is the P there, in your lineup, X, subject to some constraints. Those being lineup constraints and a budget constraint. And what we're going to end up doing is introducing what's called a robust constraint. And we do that first by pushing the original objective to the constraints using a dummy variable. Okay, so I'm maximizing the dummy, but the dummy is upper bounded by the projected points of the lineup, so I'm still maximizing the projected points of the lineup. It's still the same problem. But then we introduce this idea of maximizing actual outcomes. We can think of those actual outcomes as projections plus an error on those projections. And then finally, we make the constraint robust to a set of errors that could possibly occur, which means that that constraint has to hold true for any possible error that we could see. And for that constraint to hold true for any possible error that we could see, the dummy variable has to be less than the minimum outcome that we could see. And so when we put all this together, we're trying to maximize the dummy, but the dummy is upper bounded by the minimum scenario, or the worst case scenario. So we're trying to maximize the worst case scenario. This is how we introduce the idea of that proxy goal that I just talked about. But that problem now has an inner minimization problem that we have to deal with. We have to now solve an inside minimization problem. To do that, we first need to define what we mean by worst case scenario. We have to define the uncertainty set. There are several different ways that you can define an uncertainty set. The way that I ended up going with is what's called a vector norm uncertainty set. And I chose that for two reasons. The first is that it's computationally tractable, which I'll get into why that is later. But the second is that it's interpretable. And so this is what a vector norm uncertainty set looks like in 2 dimensions. When p equals 1, it has this diamond shape, and as p approaches infinity, the edges of the diamond push out to a box. And given this shape, we're making some implicit assumptions about our data. The first is that we're assuming that the errors are symmetrically distributed around 0, which holds true for the data that I was provided, and should hold true for most projections. Your projections shouldn't be biased. But also we're assuming that the errors are uncorrelated. You can tell by the equal area in each one of the 4 quadrants. And that does not hold true for the data that I was provided. For example, I have the errors plotted between wide receivers and quarterbacks that are on the same team. And so when quarterbacks outperform their projections, wide receivers also tend to outperform their projections, which I think makes some sense. But now when you look at the figure, there's very low point density in the 2nd and 4th quadrants, meaning we're accounting for scenarios that don't actually occur. And so our estimate of the worst case scenario is going to be too conservative. So we need to push some area from the low point density region to the high point density region. The way that I end up doing that is by scaling the errors with the inverse square root of their covariance. And as you can see from the animation, it does slightly shift some area from the 2nd and 4th quadrants to the 1st and 3rd. But now we need to put together that covariance matrix, which feels like it should be a pretty easy task, but it's not as straightforward as it seems because packages like, we'll say, NumPy don't deal with missing data very well. And so what happens is you might have this data frame of errors, and not all players play in every game. And so for weeks where players aren't playing, you just have to remove the week. But that's going to happen in many, many weeks. And so you're just going to end up with a data frame that has very few weeks worth of available data. And then your estimate of the covariance matrix is going to be pretty weak, or sometimes, frankly, non-existent. Like, you're just not going to be able to put anything together because you have no weeks where you have full data. So we're going to have to get around this issue. And what we're going to do is we're going to populate our own covariance matrix piece by piece. Okay, so I have a toy scenario to illustrate the way that I put together the covariance matrix. Let's say we're sitting in week 14, which means we're only going to be able to use data from week 1 to week 13. And the Rams are playing the Cardinals. The Bucs are also playing, but that's less important. And we're going to start with 2 points. The first is that we're going to assume that players who don't play in the same game, their errors have no bearing on each other. We're going to assume their covariance is 0. And then secondly, I'm going to start with a correlation matrix, actually, and then I'll back out a covariance matrix. And so given these 2 points, we'll initialize with an identity matrix and then populate the pairs of correlations that are between players who play in the same game. So to start, we start with pairs of players who play in the same game and who are on the same team. And those are pretty easy to put together. You have their past errors, you could just correlate them. So we do that for the sets of players who fit that bill. And then we move on to pairs of players who play in the same game, but who are on opposing teams. Their errors are correlated. In the data that I was provided, the QB, opposing QB error correlation was around 0.22. So we do need to deal with this. This isn't as easy to deal with as the same team correlations because let's take, for example, Matt Stafford and Kyler Murray. They probably haven't played in the same game yet. They literally don't have errors to correlate. And so we're going to have to come up with another way to proxy their correlation. And the way that I do it, for example, between Matt Stafford and Kyler Murray is I say that correlation is the correlation between Matt Stafford and opposing QBs over the previous 13 weeks. The one last thing about doing it that way is that covariance matrices and correlation matrices are symmetric. And so the correlation between Matt Stafford and Kyler Murray needs to equal the correlation between Kyler Murray and Matt Stafford. However, the correlation between Matt Stafford and opposing QBs is almost assuredly not equal to the correlation between Kyler Murray and opposing QBs. And so to get around this, I just employ a pretty simple rule, which is that I'm just going to select the minimum correlation between the two, minimum in magnitude, because this is the value that I'm least sure about in this matrix, and so I just want to subdue its impact on the outcome. So then I employ those sets of rules for all sets of players that play on the same game but opposing teams. And then it feels like I should have a fully populated correlation matrix. At least that's what I thought when I did this the first time. But it's not quite that simple once again. And it's not that simple because I'm going to need to take the square root of the covariance matrix later. And to do that and return real values, that matrix has to be positive semi-definite. And by definition, covariance matrices and correlation matrices are positive semi-definite when you calculate them all at once. But when you've done it the way that I've done it, there's no guarantee that this thing ends up being positive semi-definite. In fact, oftentimes it's not. And so I have to force it to be positive semi-definite. But I need to do that while keeping the values as close to the ones that I had just calculated before. And so I implement another optimization to deal with that. I implement Dijkstra's alternating projections algorithm, which projects a point onto the intersection of two convex sets. In this scenario, the two convex sets are the set of symmetric matrices with diagonal 1, as well as the set of symmetric matrices that are also positive semi-definite. So then after implementing this, the values change slightly all over the matrix, and then I have a true correlation matrix. And given that I have a true correlation matrix, it's pretty trivial to back out a covariance matrix. I just need the standard deviation on the errors for each one of the players. So now I have a true covariance matrix that I can then use to fully define the uncertainty set. And given that I have a fully defined uncertainty set, I can solve that inner minimization problem from earlier. That's that first equation that you see up there on the left. That problem is a conic programming problem, and if you're familiar with those kinds of problems, this is a straightforward solve. And so I'm going to skip over the solve to the final solution. And if you look at the final solution, it looks very similar to that basic strategy where I'm trying to maximize the projected points of the lineup, but now there's a penalty. And that penalty scales with the variance of the lineup. So if I include players that have higher individual variances on their errors, the worse the penalty. If I include pairs of players with higher covariances, the worse the penalty. So the equation makes sense, which is great. But I'm going to bring it back to the fact that this was meant to be computationally tractable. And it is for select versions of P and Q there. So for Q equals 1 and for Q approaches infinity, I'm able to linearize that objective function. And it becomes the same type of problem as the basic strategy. I've included a couple of extra variables and a couple of extra constraints, but it's the same type of problem, and so it solves very quickly, fractions of a second on my personal laptop using normal solvers. Okay, so we've talked about how we set the problem up. How does it do? Rather than trying to just test this out in a couple of weeks, I ended up running some simulations over the 2021-2022 season, which is where I was provided data. And so the errors were sampled from a multivariate Gaussian with mean 0 and a covariance matrix using all 18 weeks worth of data and the same algorithm I had just described before. And when I was optimizing in a particular week, I would just use the weeks prior to it. So for example, for week 13, I'd use weeks 1 through 12. And what I found was for some weeks, the worst case scenario wasn't improved by all that much, which can happen depending on projections and who's playing in that particular week. But for some weeks, the worst case scenario was significantly improved. And given the distributions of the basic strategy and the robust strategy and payout lines from DraftKings, I found that for the weeks where the worst case scenario is significantly improved, is improved enough that you should have gone with the robust strategy over the basic strategy. And it looks like I'm running low on time, so I will wrap up very quickly by pointing out that the results are interpretable. The solutions make sense when you see them, even though you may not have been able to come to that conclusion with all the other decisions you have to make. So this is week 16 between the robust and the basic strategy, and I looked very close except for the selection of quarterback. It went with Tom Brady over Dak Prescott. And it went with Tom Brady over Dak Prescott despite the fact he was projected to score fewer points and costed more money. And it went with Tom Brady because he had lower variance in his errors, but also because his errors are negatively correlated with teammate Ronald Jones's. So when Tom Brady underperforms, Ronald Jones tends to overperform, acting as a hedge and stabilizing the outcome of the lineup. And so I want to wrap up by saying this is not something that you use on its own. It's not a silver bullet. It's meant to be used in tandem with the basic strategy and certainly human domain knowledge, because humans are pretty good at fantasy football. This is really just a fast, rigorous framework for analyzing the trade-offs between performance and the variance on that performance. So thank you all. And I'll open up the floor for questions.
Nate was having a hard time understanding the papers, so we brought in Bill James. Bill, do you want to go first or last?
I'm happy to go first. I think everybody I'm guessing 90% of the people in the room didn't follow the math, but 90% of the people in the room have some intuitive sense of why Tom Brady is preferable to Dak Prescott just from watching the games. And first thing I want to ask you is, are the things we're sensing the same things you're measuring, do you think, or is it just a coincidence that they line up in that way?
Yeah, I think there's probably, if you watch the games and you're familiar with the play of the players, there's probably some sense of, yeah, Tom Brady's a more reliable guy than Dak Prescott, surely. It's just, as I had said before, there are lots of decisions that you have to make as the lineup manager, if you want to call it that.
Right.
It's hard to put like all of the decisions at once, lineup constraints and the budget constraint, so on and so forth.
Okay, my second question, you used the word stochastic. What is stochastic? I mean, I know I was taught this at some point, but what exactly does it mean?
Yeah, so stochastic programming is another optimization paradigm where, as I had said before, the goal is to maximize the expected payout. And so it directly deals with that problem. It maximizes the expected payout.
Right, and I'm not sure you can answer this, but I got to give it to Mike some point. It happens that at the moment, I'm dealing with a very similar problem in baseball, but without anything like your math skills. So I'm sort of not making a lot of progress, and it's been frustrating. But the problem is, since I've been a baseball writer, I've always insisted that offense and defense are equal. That the game is half offense and half defense, which doesn't turn out to be I've always known is not technically true. And the reason it's not true is that the universe is slightly asymmetrical, because you can allow a great many more runs than you can't score less than 0 runs, but you can allow a hell of a lot more than 9. So it's actually, in some ways, the same problem that making that fact work in a model is very tricky, so I wanted to ask. I don't know if you can answer this, but do you think that if I had applied generally the same mathematical line of thinking, I could reach the end of that problem by by adapting the methods you've outlined?
I'm not sure I can answer that question, to be 100% honest with you.
Okay.
I'm not baseball. I don't have enough domain knowledge. But B, a lot of what I dealt with in this problem is that things are symmetric and quite nice. And so if it's not, that just introduces some complexity that would make this much more challenging.
Thank you, sir.
Very impressive. Really great. Obviously, it begs the question, can you scale this up to be useful to actual professional teams?
Yeah, so I think if you're, to be 100% frank, if you're like a true DFS gambler and you're really trying to make a lot of money with this sort of thing, you should probably try, if you can implement your own stochastic programming, you should just do that. This is meant more for, yeah, people who own like websites and people who are a little less formal and who want something that runs quickly and that gives you solutions that kind of make some sense to you and like pressure check some of the things that you're thinking. So yeah, it's not really meant for that level of scale. Does that make sense?
But you could you do it?
Yeah, definitely.
What kind of challenges do you think you would face?
I don't think much. I think there's a couple of challenges just more broadly with the way that the problem is set up, which is that to generate the covariance matrix, you need weeks worth of data to do that. And so if you saw my results, it starts from week 10. I used the first half of the season to generate the covariance matrix. And so that's kind of an issue. There are ways that you can deal with that, but dealing with that with a lot of data is just it can be more complicated.
Gotcha, thank you.
My question is more about that technique that you just were talking about around generating your own covariance matrix. So the step before that showed missing data. So you have weeks where you have missing data if players didn't play. Did you consider other imputation techniques and not directly solving it at the covariance matrix level?
Yeah, so I did consider other imputation techniques, like you could, I don't know, use a median error and plug those in, or just directly trying to predict the error. But I didn't want, with the predicting the error technique, I didn't want to try and predict the error. It felt like it was, like there's already quite a lot of issues that I'm trying to deal with, and I'm putting my own sauce on things, if that makes sense. And I don't want to keep adding a bunch of things to the point where it's like maybe not, the solution doesn't make sense. The answers that I'm seeing are struggling. So I just wanted to use the set of data that I had.
Okay, and that maybe relates a little bit to my second question. You talked about having some kind of ability to interpret what the model is suggesting, and at the same time, speed is of top of mind, and,
Yes.
and the clear motivation for why you're doing this. So really, is interpretation that important? Is anybody going to pause as much and look at that? I'm just curious to how you find that right balance between those two.
Yeah. I do think interpretation is important because a lot of times what folks will do, especially if they're kind of just optimizing lineups on a website themselves, some of these websites will have the ability to, we'll say, stack players where they have a quarterback and wide receiver must be on the same team. They'll add their own rules or they'll add whatever. And the ability to run it quickly, see the result, and say, is this what I'm thinking? If not, why? Because that's the point that a lot of DFS players have a lot of fun is, I see the solution, why is it not matching my intuition because I'm so smart at this kind of thing. So yeah, I think interpretation is important.
Terrific. No notes. But I do have some questions. So the first is that, so you've looked at these two cases. One is the basic where you're trying to maximize the mean, and the other is your robust method where you're trying to minimize the tail that's on the other side of the payoff line.
That's right.
Those are two extremes, and you could certainly do something in between. Like you could say, okay, I care this much about the mean, but this much about the tail, and just make a Pareto front, which has got like a mean and this tail. Have you thought about that and how you might where you might want to sit on that continuum?
I have not thought about that. It's a great idea, by the way.
Thanks.
And something I would consider doing next, yeah.
Awesome. Okay, here's another suggestion for next. So this was for 50-50s. If you're playing in a tournament where there's only payout to the top 10 or something, you want to do the inverse, where you have some threshold here and you want to maximize the tail that's on the upper end. Have you tried this to see how well this might do in tournaments? And do you get different lineups if you're using that as your objective?
Yeah, so you can. There's a minus sign in there, and one of the formulas, you can flip that to a plus sign, and it would do what you're talking about. It would defeat the purpose of what I was trying to go for, because that problem is no longer, I can't linearize that objective anymore.
I see.
And so it's just going to be a really hard problem for the solver to deal with, and then it would be the same as a stochastic programming problem.
Got it,
So
okay.
I didn't worry about continuing down that path.
Okay, great answer. And one more question. This is again to the covariance matrix. So after 6 weeks, you sort of try to impute those values in the covariance matrix. But then the next week, you've filled some of those in because you've had another week of people playing. So you can check how well you did the previous week. So if you do that as you get more and more weeks played, how good was your guess at the covariance matrix?
Oh, that's great. No, that's not something I actually tried doing to
Yeah.
compare in the past, but
Okay.
something I would do.
Yeah, great. All right, thanks.